we've got our last keynote of the day coming at us. Where you at, Tengyu? Where you at? Where you at? Oh, closing doors, making sure that we got the vibe right, huh?
Yeah, I'm at Stanford. Actually, I'm at home.
Nice. All right. I like it. I like it.
Yeah,
So, man, I'm excited for your talk. I appreciate you closing it out for us. This is very, very awesome. I'm honored to have you at this virtual conference. And I'm going to just hand it over to you. And anybody that wants to ask questions, feel free to drop them in the chat. We're all here now. And so I'll try and grab the best questions and then shoot them at you when you're done.
yeah. Thanks so much. Thanks so much for having me here. I guess you can hear me okay. Yeah,
Yeah.
this is a great event. Yeah, so this is the first time I hear a song before the talk, and also maybe original song. Next time maybe, maybe this is the last time I'm gonna hear an original song before a talk. So yeah, it's really nice to be here. And my talk is about RAG and some of the a little more advanced techniques on RAG. Let me just make it bigger. So I'm Tengyu. I'm assistant professor at Stanford. I'm also having a startup right now. I'm the co-founder and CEO of Voyage AI, who is mostly working on the components in RAG. So I'm trained as a scientist, and I know that this is a data engineering conference. So I try to make the talk more technical. But I guess technical doesn't necessarily mean that more engineering. I guess you'll see. So I would like to start a talk by very, very briefly talking about what I see as the paradigm change in engineering and in just generally like how things are deployed in industry. So like about like 5 years ago, 7 years ago, I started at Stanford. I started teaching this course, CS299 machine learning with Chris Ray, my colleague at Stanford. So, and in the slide deck, there was a slide which is like this. So the 7 steps of ML systems: acquire data, look at your data, so on and so forth, and you repeat. And we still teach this actually. So I occasionally use these slides to teach that lecture. But actually, in the foundation model of generative AI era, it sounds like one gigantic pre-trained large language model can do just almost everything. You know, all of these steps are required when you build a model. But once the model are ready, you don't really need any of these steps. You just a large language model can simulate most humans in many cases. And so this makes the kind of the paradigm a little bit different, because now you are using these modules or the models as a black box without thinking too much about deployment, because most of the calls are API calls. Even you host the model on your own infrastructure. Actually, you still try to set it up so that you do API call to the models. So and the way that you really do is that you describe the task in natural language and write some instructions and demonstrations, not very different from training a new employee, onboarding them in your company. So so in some sense, the tasks becomes more like how do you write up good instructions in natural language, as opposed to writing up the code to train the model and like measure, so on and so forth. So however, the issue is that an off-the-shelf large language model doesn't and shouldn't know your proprietary data, and that's still missing. So even you have an employee who is really, really smart, they cannot really just work at the company from day one, because they don't have the institutional knowledge about the company. They don't know the data in the company. They still have to learn something specific about the company. And I think that comes the another layer on top of large language model, which I'm going to focus on. So my view is that even large language models approach AGI, even you have Einstein, you still need some retrieval system, some knowledge system that help you in addition to that ingest the proprietary and unstructured data from the proprietary environment, like a company. So, and that's where the RAG come into play. And this is the probably a predominant approach these days. After like 1.5 years of discussions between different approach. So how does RAG work? I assume most of the audience roughly know how it works, so I'm going to be very brief here. So basically, you have unstructured proprietary data, and then you go through these 4 steps, which are for retrieval, retrieving relevant information. And once you retrieve relevant information, you give them to a large language model. And these 4 steps are, first step is ETL, where you have to connect to the data sources and then transform the data in a way that can be processed by a text embedding model. So basically, you just turn everything into text so far. So you get a JSON file out of this ETL step. And then you use the embedding model to vectorize the text. And then you get a vector. And if you have a lot of documents, of course, you get a lot of vectors. And you put these vectors into vector base for it to organize, store, and then you do a search using the vector database k-nearest neighbor search module. And then you got, probably 100 documents that are relevant to the query. And then you use a reranker step or re-ranking step to refine the results to probably top 5, top 3. And you give the top 3 documents to large language model. And the ETL and the vector database steps are mostly engineering, I would say, because they don't necessarily change the quality of the search results. And embedding models and re-rankers are the AI components that decides the retrieval quality, and also they drive the end-to-end response quality. As you know, if you don't have the relevant information, then the large language model may hallucinate because they don't know how to answer the question. And if you have the relevant information these days, even relatively weak large language model can synthesize a good answer given the relevant information. So I like to spend probably like 2 minutes to discuss, some of this. I think these days it becomes much clearer. RAG versus fine-tuning versus long context. These are 3 ways to incorporate proprietary information into large language model. I think there's still probably some debate there, and this is my view. I like to start with, giving an analogy with the biological networks. So RAG, in some sense, is analogous to you retrieve and read some books from a library to solve a problem. Fine-tuning is kind of like you work so hard to rewire your brain even, right? Because you change your parameters, in some sense, you change your synapses in your brain. You rewire your brain so that you are very, very good at some type of problems without even additional context. Your brain just memorize and, in the synapses, those kind of like type of problems. And long context is kind of like you read the entire library in your short-term memory in your brain every time to solve a problem. And from the analogy, you can kind of see the differences and pros and cons, right? So fine-tuning, if it works, is great because you don't have to have any additional context every time you run the solve a new problem. But it's very kind of like requires a lot of like knowledge to really change your brain, how your brain works. And that's kind of the challenge in some sense these days with fine-tuning, because without enough data, fine-tuning doesn't seem to be very effective. You may not be able to ingest the knowledge into fine-tune the model, or you may overfit to the small amount of data. And for long context, it's really just costly, right? It doesn't seem to make a lot of sense to read the entire library every time to solve your problem. So if you look at the details about cost of RAG versus long context, this is my off-the-shelf calculation. I didn't do a very careful calculation because the gap is too big. Right? So assume you have 1 million tokens. A query of a RAG doesn't really scale with the number of tokens because it only depends on how many tokens in the query there are. So that's probably on the order of 1e minus 5, because 100 tokens times most of embedding models these days is 1e minus 7. So 100 tokens times 1e minus 7 is 1e minus 5. And a query with a long context with 1 million tokens costs probably $10, because let's say 1 million token times most of the large language model is something like 5 tokens per million token, maybe $10 per million token. So it's 1e minus 5 on that order. So you have 1 million times 1e minus 5, which is kind of like $10. So the gap is like a 6 orders of magnitude. Of course, you can cache the activations of the long context transformer, but the storage costs are also significant because you have to keep the GPU running there. You have to store them in some other ways, you can probably shave off a few magnitudes, from the long context, but there's so much of a gap. Long context, large language models may become cheaper and cheaper because of other issues, other factors. For example, the GPUs may become cheaper. We may have better engineering to maximize our MFU, the GPU utilization, or other tricks to speed up things. But most of those tricks also applies to RAG, and so which means RAG will also get cheaper. So basically, this is my personal view. Long context is just way too expensive. Fine tuning doesn't seem to work after, or doesn't seem to work very well with not enough data after 1.5 years, of kind of like, in the last, fine tuning has been there for a long time, but in the last 1.5 years, I think people have tried it a lot and it doesn't seem to work very well. And RAG seems to be the future direction to go, and it makes sense. It has this hierarchical structure where you first retrieve some information, a small amount of information, and put in your short-term memory, and then solve the problem, and you forget about them. And next time you retrieve some other small amount of information in your short-term memory, which means the context, and then solve the problem. So yeah, so that's RAG, and the rest of the talk will be a little bit more about some of the details about how RAG works and how to make RAG works better. So very, very briefly, so embedding model, which is the key part here, is these models that vectorize documents or queries into vectors. So every document will be mapped to a vector, which is a list of numbers, which is called vectors or embeddings. So every document or queries will have a vector representations in the Euclidean space. And so let's say it's 3D instead of like in reality it's going to be a 1,000 dimension. But let's say the vector is 3D, then basically it's a point in the 3D space. And the properties that you have about the embedding model is that the relatedness or the semantic relationship between documents is captured by the geometric distance between the vectors. So if you have two documents that are close in the geometric space, they are also close in the semantic space. And that's why you can read off the semantic relationship by looking at the geometric distances between two documents. And that makes it useful for semantic search. So basically, you want to search similar documents, just to do k-nearest neighbor search in a geometric space, right? You give a query, you're given a query, and you turn the query into a vector in the same space, and then you look at which are the closest vectors to the query vector and among all the document vectors. And you found document 3, and then you say that's the most related documents in the semantic sense. And another component, which is slightly less popular, but most of the Sphinx users are using, is the rerankers. So this is the fourth step I had in the RAG stack. So this is an additional refinement step on top of the vector search, right? Suppose you have already done a search, let's say vector-based search, or sometimes people use lexical search like the BM25 to do the search. And you already get 100 documents. And then you can still re-rank these 100 documents. Maybe you don't know whether these 100 documents are ranked correctly. Maybe these 100 documents are obtained through multiple sources of search algorithms, or you just want to refine them. And then you can use this ranker, which basically takes in a set of documents and then re-rank them and give a relevant score for every document. And you can use the scores to sort the documents and then take a subset of them. So you sort them and you take maybe top 3, which are the most highly relevant documents among this stage. So it's a refinement step. And why re-rankers is useful is because there's some structural differences in how the neural networks are implemented under the hood. So if you use embedding models, just to recap, so you have a query and you go through a transformer, which is the embedding model, and then you get a vector out. And you are given a document, you go through the transformer, you are getting embedding out. And then only at this point, the interactions between the query and the embeddings, or the queries and the documents start to matter. So only at the end, you take a cosine similarity and you have interactions between the two objects, the query and documents. So the benefit of this 2-tower bi-encoder setup for embedding model is that the embeddings or the vectors for the documents can be pre-computed prior to query time, and that saves a lot of time in your on the fly, right? But the problem is that when you compute the embeddings or the vectors for the document, it doesn't know the query at that time. So basically, the embeddings has to be prepared for all kind of possible queries, and that creates a lot of burden in the embeddings, because the embeddings basically have to the embeddings for the document basically have to memorize almost every aspect of the document, so that you can be prepared for all kind of possible queries down the road. And that just creates a lot of burden to the embeddings, and which means that you may not be able to memorize all the details of the document. However, when you have this reranker, the reranker setup is that at the time that you have the reranker, you already have a small set of documents, so you can afford to concatenate the query and document together and give it to the a transformer together. So it's called cross encoder, as you can see from the figure. So basically, this transformer sees both the query and document, and that means that you can quickly drop all the irrelevant part of the document and only focus on the relevant part and really process very carefully whether the document is really relevant to the query. So basically, you have more focus because the query is given to you when you are processing the document, and that's why the rerankers can give you very high, highly accurate relevant scores. But the downside is that you have to see both the query and document, and so basically at the query time, you have to run this multiple times, depending on how many documents you want to process. So you cannot really process 1,000 or 1,000,000 query plus document pairs. You can only probably process 100 of them. That means you can only work with 100 documents, and that's why you need a pre-filtering step from the embedding models to pre-filter 100 documents and then give it to a reranker. So reranker is much more accurate, but also slower. So that's why you can only use it for a small number of documents. Okay, so these are some of the basics, and now let's discuss a little bit about how do we improve the retrieval quality, which is one of the I think it's the main bottleneck these days for RAG. You don't retrieve the relevant document or information, then you don't have a good answer. And in many cases, the information is there in your pool of data, but it's just that the embedding models and rerankers couldn't find them. And I'm listing 6 or 7, 8, I think probably 8 suggestions, which are some of the aggregations of all my past experiences and talking to our users and other people reading blog posts. I will summarize, which one is probably more likely to work at the end, but I will go through some of these techniques quickly. I didn't have citations here, but I think most of this, you can just Google search it and find some relevant information online. I don't want to kind of like promote some references without carefully going through them. So that's why I didn't have the references. So the first one, which is mostly commonly used, is the query generation and decomposition, which means that you somehow say, oh, the culprit is the query is too simple, so that nobody can understand what the queries means, or at least you should help the embedding models and rankers to have more unambiguous and detailed query. So for example, if your original query is RAG, sometimes users just type the 3 letters and expect to give a high quality answer. And then you can extend the query to please explain more details about retrieval-augmented generation. A parenthesis is RAG, right? So this will give more information to the embeddings, and if the embeddings are not so strong, this will help a lot, because now the embedding models will see a lot of more keywords and helps the matching a lot. And how do you do this? You can use some rule-based methods, or you can use the ChatGPT to extend the query, so on and so forth. And sometimes if you're making multiple queries, you can say, please explain the retrieval step first, please explain the generation step first. How do you generate multiple queries? Sometimes you can use a large language model to say, oh, given this original query, can you give me 3 a more detailed query with more step-by-step kind of queries? And there are many different ways to do this, if you search online. Another way is that you can do something similar in the rerankers, where you can but not kind of by changing the queries, but just by adding some instructions. For example, you can say sometimes the challenge is that the similarity definition is not clear upfront, right? Different people have different similarity definition of similarity. And the embedding models and the rerankers don't know what's your definition of similarity. They will just guess the most common sense definition of similarity. But you can always give some instructions to the in the query on what the similarities you care about, right? You may care about similarities in only the content, or maybe you care about similarities in terms of the entity names are mentioned twice in both the query and documents. You may care about some other definition of similarity. You can say that in your query. This depends on whether the rankers are responsive to it. Sometimes they don't, but you can give it a try. Another pretty commonly used one for sophisticated users is iterative and recursive retrieval. And kind of the rationale there is that sometimes your documents have links to other documents, right? Or the ideal document cannot be found in one step. So in design workflow that retrieves documents iteratively, you first retrieve probably the most nearby documents, and then you retrieve documents that can be linked to the initially retrieved documents, or those documents that are similar to the initially retrieved documents in some other sense. You can make this rule-based, you can make this large language model driven, you can use embedding models again for the next time for retrieval. Again, I don't want to go into too much details here because it really depends a lot on case-by-case situations, depends on our data. Another dimension people explore is how do you trunk the data properly, right? So these days, some of the embedding models have very long context. For example, in my company, Voyage AI, we have 32K context, which we are proud of. But it's not always that the longest possible context is always the best. Maybe sometimes like 5K, 10K is better than 32K. And the reason is that if you reduce the trunk size, then you can retrieve more trunks with the same downstream cost. And if you're sensitive to downstream cost, then it could be possible that you want to use smaller trunk in return with more retrieved trunks. And when you have more retrieved trunks, then there's a more chance that you hit something useful. On the other hand, if you have increased trunk size, then your trunk will be much more self-contained, and they are more easier to be retrieved. And you have to balance these two factors. For example, if the trunk size is 512, often I feel like it's probably too small because you don't have enough information there in each trunk. Then you may kind of like the models may misunderstand the trunk so that they don't retrieve them. But 32K, it depends on whether you really need it. Sometimes people don't need it. Sometimes people are cost sensitive, so they still want to have smaller trunks than 32K. Okay, so the next slide have some, personal suggestions that in my view that are on a slightly different level. So so these are okay. So number 5, maybe as you can see, from kind of like some of the discussions before, you may want to look at data and find out where the issues are. So and then fix them as if you're talking to a librarian, right? So that's kind of like how people come up with the first 4 methods, right? So you found out that your issue is that it doesn't deal with the links very well in the documents, right? So then you actually like intentionally or explicitly help the model to use the links and do some recursive kind of like retrieval. Or you find out that it's because that sometimes actually I forgot to mention this. Sometimes people also put the headers in every trunk. So even though the headers or the titles of the document is not necessarily part of the trunk naturally, but you always say no matter where the trunk is in the document, you always copy the document title and append it to the trunk. So and what's the rationale for that? That's because some people look at their data, they found that the trunks are not interpretable anymore, even by humans, if without the title of the document, right? You don't know the context. For example, you have a legal document, and you know that in a legal document, after the first few paragraphs, the company, the two parties are referred as maybe the licensor, the licensee, the partner, so on and so forth. The company's name never show up after a certain point, right? And if you have a trunk that doesn't have those kind of like indicators, oh, I guess I'm out of time. So then I'll wrap up very quickly. So if you don't have those company names, then the trunks are not meaningful because you don't really know which companies these documents are, the trunks are about. So that's why you have to copy the first paragraph with the trunk. You have to kind of like copy paste the document title together with the trunk, together with the trunk. So sometimes you just found out that actually you just need a better off-the-shelf embedding models and rerankers. For example, you probably can try general purpose or domain-specific embeddings by Voyage AI. Sometimes you can fine-tune the embedding models if you have a lot of pairs. And here the idea is you have these positive pairs which has semantic relationship, which could be like title, document, question, supporting evidence, caption, image, and then use these simpler logs to fine-tune the embeddings. Or you can use some of the APIs, or use some of the companies to fine-tune the embeddings for you. For example, Voyage. The last dimension I want to discuss is that you also need a proper evaluation data set. Even you have done all the 1 to 7 in the past few slides, you also need a proper evaluation set that can check which method works, because there's no method that can just work, guaranteed to work without any experimentations. Maybe using a better embedding models, that's probably always guaranteed to work, but still you want to check whether it really works before deployment. And there are some ways kind of to create data sets. One way is to create a labeled retrieval data sets. In the interest of time, I mean, not go into the details here. Another way is you can use large language model as a judge. You basically do a shootout, use the large language model to decide which document is relevant. The only thing is that you have to anonymize the model names. You have to randomize the order. We have seen people using the fixed order, which create biases. And there's some pros and cons there. It's cheaper, it's simple and cheap for one test, but it could be expensive because you cannot reuse the data sets. Okay, just as a summary, so retrieval augment and RAG, in my opinion, is always needed, even when large language model approach AGI. Embedding models, rankers are responsible for the quality of the retrieval, and I've discussed the various techniques that I'm aware of to improve the retrieval quality. So I think the challenges here are, one is that some of the domains have very, very specialized jargon and knowledge. I've seen some of these from my customers. And I think here you probably just have to, for example, if you have a chemistry document, most of the embedding models wouldn't understand enough about the chemistry terms. And now you need either domain-specific models that are really customized for your domain, or you need fine-tuning on your data. Sometimes another issue I've alluded to is that the trunks, don't know the global context, and you need some embedding models that somehow know additional context about a document, as opposed to just to do this hedgehog thing where you copy paste the headers or the titles to the trunk. We're going to release some models that have these properties. And looking forward, I guess I think the community to make this community really mature, I think we need something that is really standardized and clean tech stack that can always achieve about, for example, 95% retrieval accuracy. We are probably not exactly there yet. In some data sets we have that, with some of the advanced embedding models and some of the techniques. But for some other cases, the retrieval accuracy is probably still below 95%. And then you start to kind of doubt whether you can use this in production, right? And then probably a few years later, the goal of the community probably is to improve from 95 to 99 or 99.9 accuracy for the retrieval. That's all I have. Thank you so much.
Well, thank you, sir. That was awesome. And no need to rush because you are the final keynote, so you get all the time in the world. But there's
Thanks.
a lot of questions coming through in the chat, and rightly
Yeah,
so.
we'd love to
So
answer
many
some.
cool questions. One, let me see what the first one is. So many. I'm scrolling. All right. Um, I imagine the embeddings will change based on how you break your documents into chunks, and it's hard to know what the optimal breaks are in advance. Any tips on how to deal with that?
Yeah, so I probably was a little bit fast there when I was talking about this. So um, I think so first of all, Voyage AI. Sorry, I'm talking about my own company a little bit too much. We are going to release some automatic trunking strategy so that you don't have to worry about this in the future. After we have launched this product, if you use it, you're just going to send us a document and we'll do everything for you. And actually, it's the machine learning model that does everything for you to decide the optimal trunk. But at this moment, I think um, pretty much you are thinking about these two factors. So what's your cost structure, right? Do you really want to send very very long documents to GPT-3, GPT-4, or Anthropic cloud? If you don't want that, you probably should have smaller trunk size, right? And but if you have bigger trunk, oftentimes the performance is better. If you measure the same number of trunks, but not measure the same number of tokens, and especially if you use embedding model that are really truly responsive to long context. Some of the embedding models, they claim they are long context, but actually when you have long context, they miss information in between. But if the embedding models are really truly responsive to long context, increasing the trunk size is almost often better, as long as you don't care about the cost. Um, um, yeah, but there's some trade-off there. So yeah, sorry, the answer is really just that intuitively this is the trade-off. Um, um, but eventually you need to do some experimentations with evaluation to know what's the right trade-off you want to choose, and
Yeah.
between cost and quality.
The other thing that I think I've heard some people talk about is how you can get really messed up by cutting off a chunk in the middle of a sentence or the middle of a
Yeah.
paragraph. Have you found any ways to help against that?
Oh yeah, that's actually relatively that it's not trivial, but it's a soft task to some degree now because there are some of these online packages, or some of the companies like unstructured Llama Index, and some of the open source code, which can let you to not do that. You just say my trunk size is about 2,000 tokens, but I don't want to break any sentences or even documents or even sections.
Uh-huh.
So and then they will do it. They won't satisfy exactly 2,000 trunk size, but it will be approximately 2,000 trunk size. And another thing is you can have some overlap to also mitigate this issue. I think that mostly gets solved with these kind of techniques.
Nice. How often do we need to retrain our RAG pipeline with the new documents getting added in?
Um, One of the benefits of the RAG is that when you have new documents, you don't have to retrain anything. You just have to vectorize the new documents and put it into the same system. So there's no retraining. It's really just adding more documents to the pipeline. So the only thing you have to do is vectorize all the new documents, put them in the vector database. That's it. That's it. Um, but maybe sometimes you want to change your embedding models, right? You want to change the components you are using, right? So I think for that, maybe like a few months, like maybe a year would be the right cadence, because embedding models um re-implement their rack stack too often. I think most of the embedding model providers also release new models probably on the order of like 6 months to one year.
Uh-huh.
And that's at least what we are doing at Voyage. Maybe OpenAI is even a little bit slower. So that's probably the time that you can consider changing your embedding models to improve the quality.
Is reindexing mutually exclusive with re-ranking, or are they different?
Uh, there is no mutually inclusive means no. Reindexing is a way to revectorize your. Maybe let me go to the I guess it depends a little bit on how you how you define this. But basically, these four steps are all all more very very modularized, right? So at any time you can replace your embeddings and by other embeddings, you can replace your rerankers by other rerankers. The only thing is that if you replace your rerankers by other rerankers, you don't have to do anything. Basically, you just change that line of code, you call a different API, and that's it, because it's stateless, right? Every time you run a reranker, you can forget about everything you have done. for embedding models, it's slightly more tricky to change, because if you change the embeddings models, you have to change all your vectors that you have vectorized. Basically, all the vectors you have got from the documents, you have to be re-vectorized. So basically, you say I change my embedding models to some other models, and I use that new model to go through my entire document base and vectorize all of the documents and put them into the vector database. And I remove all the old information. It's not that hard, it takes probably a few hours. But yeah.
But I imagine it does have a bit of a cost component to it, so you have to think about that. And
Exactly. Even though the cost for embedding models these days is often a smaller fraction
yeah,
of the entire rack stack, you will spend much more money on large language models. That's why, at least at this moment, unless you have like 20 billion tokens, it's not that expensive yet.
yeah, yeah, I can see it being like kind of that trade-off where new model, new, you think about, all right, do we want to run all of our documentation through this new embedding model, or do we want to just wait? Like, what's the performance versus cost trade-off that we're looking at?
Yeah. Another dimension that is interesting is the following. So you replace your embedding models, but you could possibly save your cost for your vector database, because this depends on, for example, suppose you use a smaller embedding model which has the same performance, and the smaller embedding model will give you smaller dimensionality of the vectors, and
Uh-huh.
that means your vector database cost will go down linearly in the dimensionality of the vectors, right? So you actually may save something, even though you have to vectorize your document
Yeah,
again.
yeah. But then do you see the performance also go down?
No, you could use your, sure. If you just use you need to use a model that has smaller dimensionality but the same performance. Basically, I'm saying, like, suppose, for example, on the market there's a new
I
model,
see.
and this new model is better or the same performance but smaller dimensionality, then you should consider using that, because it can save your cost for other components.
Yeah, makes sense. And then the last thing that I wanted to ask was around fine-tuning your embedding models. And I know there's a lot of like really cheap ways to do that
Mhm.
these days. It feels like there's some stuff. Even I've seen people do it like with BERT models, right?
Yep.
And how, so for you, I think one thing that I imagine you get asked a lot is like, why wouldn't I just fine-tune a BERT model?
Yep. Yep. So we got a lot of those questions, and people tried it and it didn't work very well. In
So
some
basically
cases
you
it
say
could work.
go try and fine-tune a BERT model, and then I'll talk to you in a few weeks.
Yeah. I think the answer is that, um, I wouldn't say like it's never works. I think it always give you some lift on top of BERT. When I say it doesn't work, it means that it doesn't give you enough performance gain to beat even sometimes off-the-shelf embedding models without fine-tuning. The reason is the following. I think in my of course, this is not like it's like, as a scientist, I probably wouldn't be able to say this, with strong evidence, but I think my intuition is that, so basically, your final performance after fine tuning is so basically the fine tuning is mostly trying to understand the style and and the preferences of the user's queries. So basically, users' queries sometimes are ambiguous, but in
Uh-huh.
certain cases, you have the context, right? So basically, maybe suppose you talk to only kind of like high school students. They have a different way of using the language, and your embedding models don't know it, right? So then, if you fine tune, you start to know their kind of rules and their abbreviations, all of those. So those are very easily obtained by fine tuning. But fine tuning, so far, I don't see a strong evidence that fine tuning can gain a lot of knowledge, like a hardcore kind of factual knowledge, uh, if you only fine tune a small amount of data. So
Uh-huh.
basically, if you have a lot of data, then you can fine tune and really gain a lot of knowledge, and then you can have a substantial lift. But if you don't have a lot of data, then you are mostly just learning the styles. the styles also give you, the styles and preferences will give you probably 5 to 10% improvement, which is, very good if you start with a very strong embedding model. But if you start with BERT, 5 to 10% improvement is not enough for you to go
Yeah,
above the off-the-shelf embedding models, the strong embedding models, if that makes sense.
100%. Well, thanks, dude. This has been great. I want to thank you so much for doing our final keynote of the day. This has been awesome.
Thanks so much. Yeah, it's really fun to be here.